So the divergence theorem, also sometimes called Gauss's theorem, although that's not a great name for it because Gauss has like a dozen theorems named after him. So the divergence theorem is for relating integrals over 3D solid regions with their boundaries. And so we're going to assume that the boundary is positively oriented. This means that the normal vector is going to be pointing outwards. And we assume also usual standard assumption that our vector field is reasonably nice. So smooth meaning, continuous derivatives on some neighborhood containing the set we're interested in. All right, then the divergence theorem says that the double integral over the boundary of the region of the normal component of the vector field is equal to the integral of the divergence over the entire region. And so this you should think of as being a higher dimensional analog of Green's theorem. So if we compare it to the flux version of Green's theorem, it looks like this. We've got the integral over the boundary of the normal component of f dot ds, where s is the arc length element traveling around the boundary of some region R, and that's equal to the integral over the entire region R of the divergence of f with respect to area. So you can see they're extremely similar here. And also, just like for Green's theorem, since we are looking at the normal component, because we're dotting against a normal vector here, that means that these are going to be useful for computing flux, because we're looking at what's going transversely across the surface. So I mean, if the surface looks like this, then we're looking at the component of the vector field that's moving transversely across it.